So first off, we are going to find our unknowns and our knowns for the closed system of the water problem. And so first we're gonna just make a container here. And that's our container of water that we have. And one of our unknowns is the total volume. So we're just gonna call that VT. And then that is unknown. And then we're also looking for the final temperature, so TF. And then our knowns, one of them is our initial pressure, which is PI, which is 101.325 pascals. And that is equivalent to 1 atmosphere, which is what it gives us in the problem. And then we also know our initial temperature, so TI, which is 298 Kelvin. And then another known is our final pressure. And in the problem, it gives us 2 bars, which is equivalent to 200,000 pascals. And then we also know the total mass of water in the container, which is 1 kilogram. So we're gonna do M W tot, which is equal to 1 kg. And then we also know the moles of water vapor in our container. And so we got our moles of water vapor, which is equal to 0.3 which is equal to 0.3 moles. So now I'm going to simply show that this will be the liquid water, and this will be vapor water. And basically, VT is the total volume of the water in the vapor phase and liquid water. So I'm going to write that in an equation. So it'll be VT is equal to VL plus VV. So that's the volume of the liquid plus volume of the vapor, which is the total volume. We also know that we have the total water, or the total mass of water here, and the total mass of water here will be the mass of water in the vapor phase plus the liquid water. And so we're going to write that down as an equation, and it's going to be mass of the total water is equal to the mass of water in the liquid phase plus the mass of water in the vapor phase. And then we also know that this is the mass of vapor water in moles, and we can use the molecular weight of water to figure out what that is in kilograms. And the molecular weight of water is 18.02 grams per mole, but we're going to convert that to kilograms, so we're going to multiply this by 18 to the negative third, and that is kilograms per mole. We also know that the final pressure is the pressure of water plus the pressure of the air. So we're going to write that down. So we're going to do PF is equal to PW plus P air. And then the pressure of the water can also be determined by Antoine's equation, which is do log 10 P equal to A minus B over C plus T. And then so PW will equal, basically we're solving for this P, or this pressure right here, and this temperature will be the final temperature, which is also an unknown. So it'll be 10 to the A minus B over C plus TF. And that is the pressure of the water. And then P air can be solved using the ideal gas law, which is PV equals nRT. And this N is going to be the moles of the air, and then this temperature will be the final temperature, or unknown, and then this volume will be the volume of the vapor. So let's solve for P. So P air is equal to N air, which is the number of moles of air. Then R is our constant. And then we got our final temperature all over the volume and the vapor phase. And another equation that'll help us out a lot here is one that involves the volume of the liquid, or the water in the liquid phase, and the mass of the water in the liquid phase. And obviously you can just use the density formula for that. And so we're going to write that down here. And so we got density of water in the liquid phase, and then we have density is mass over volume, so it'll be mass of water in the liquid phase over volume of water in the liquid phase. Now we can also use this in order to find the volume in the liquid phase, because this will equal the mass of water in the liquid phase over density of water in the liquid phase. And this right here also equals the mass of the total water minus the mass of the water in the vapor phase. So this equals mass of water total minus mass of water in the vapor phase. And then that'll give us this formula that we can use. That equation helps out a lot because we know the total mass of water, which is 1 kilogram, and we can also figure out the mass of the water in the vapor phase by using these moles and the molecular weight of water, and we know the density of water to be 1,000 kilograms per cubic meter. So now we are going to create a equation using the initial moles of air. And so that, we're basically just going to solve for N over there. So it'll basically look like N air equals, and then it'll be the initial pressure of the air. So it'll be pressure of air, and then I times EV, which is the volume of in the vapor phase, over R times initial temperature. And then what we can do with this is we can use the, oh sorry, you probably can't see that. That's what it looks like. And then what we can do with this is we can plug in the initial pressure minus the partial pressure of water at the initial temperature. And then that will give us, that is equivalent to this. So it'll be initial pressure minus pressure of water at Ti, and then that will be multiplied by the volume in the vapor phase. But using this, we know that the volume of the vapor phase is equal to the total volume minus the liquid volume. And so to make it easier on ourselves when we go and code, I'm going to plug this right here into VL. And then it'll be VT minus mass of total water minus mass of water in the vapor phase over the density of water in the liquid phase. I kind of ran into that equation, and that will all be over R times Ti. So what that equation does is it gives us our total volume in an equation that we can then use to eventually solve for the total volume, which is one of our unknowns. And we'll do that in Colaboratory. Then we are going to also use this equation to then get an equation where we have TF, and then we'll eventually solve for TF using Colaboratory. And so what that looks like is that will be instead of the moles of the air, it'll be the moles of the water in the vapor phase. So it'll be NWV is equal to, it'll be the pressure of the water at the final temperature times the volume in the vapor phase. And by then we'll know the volume in the vapor phase because we will have then solved for both of these two. And then it's over R TF. And then remember, this is equal to 0.3 moles. And then that's our equation to find our second unknown, that is TF. So I actually made a mistake the first time I went through this, and instead of plugging in the total mass of the water over the density of water to get the volume in the liquid phase, I just plugged in what I got for VL, which was the total mass of water minus the mass of water in the vapor phase. But at the initial temperature, there's no water in the vapor phase. So that's why that was wrong. And I'm pretty sure somebody asked it in class. And that's why I caught it, because I was rewatching one of your videos and I noticed that I got something a little bit different. Now that we are on Colaboratory, we have a repository on GitHub that we want to use, and it's CHE Tools. And so what I'm going to do is copy the URL to this repository, and then we want to clone it onto the Colaboratory hard drive. So we're going to do git clone, and then this depth 1, basically all that does is it just pulls the latest version of the repository, because Carlos has edited it 100 times, like hundreds of times. So we just only want the latest version, not all of them. And then we paste the URL in here, and then after that we want to actually be able to use this. So we are going to import sys, and then what sys does is it changes the path that Python takes to get to your given file. So we're going to do sys.path.insert, and this one right here moves our path that we're about to type in to the first one on the list that it checks. And so I already ran it on here, so that's why CHE tool isn't popping up. And so the path that we took is going to be content, /content, and then /CHE tools. And then that is our path. Shift enter, and it does this because I already have it in here. Now we have to import CHE, and because we're lazy, we are going to do as CHE, so that instead of having to type tools.che, we can just type CHE. Then we are going to create a class and also create an object with it, or instantiate. And so we're gonna do che.props, and then we are going to only be looking at water in this case. And oh, that needs to be capital W. And then we can do this. And then what that allows us to do is we can do z this, and this is all of the data in the data sheet that I showed you earlier, that any information about water you could possibly need, you have right here. Like for example, we could do this, and but you need to supply a temperature, so we can do this, and then this is the density of water at 298 Kelvin. So because we have two equations and we also have two unknowns, we have to use a root finder. So to use a root or a root solver, sorry. And then you have to do SciPy optimize import root, enter. And then while we're at it, we'll just define R, because I know we're gonna have to use R at some point. So 8.314. So you gotta remember with the root function, you have to provide an initial guess, but the root solver also requires two functions because we have two unknowns. And so what we're going to do is we're going to define our functions. So we're going to do define, and then we'll just do equations, and then this, when it returns it, the root solver will return it in vector form. So we're just gonna call this vector, and then this vector will return the two unknowns. So we are going to unpack that. So that'll be our final temperature as our first unknown, and then our second unknown will be VT, which is the total volume in the container. And that's unpacking it. Then we want to return something. So we are going to return the final pressure minus the final pressure that was given to us. So I'm just gonna call that final pressure, or I shouldn't say given to us, but like more that we want to get to. So that's one of our parameters to the problem that has to satisfy the other equations. So it'll be final pressure wanted And then that is one of them. And then we also have the parameter of the moles of water in the vapor phase. Like the final moles of water in the vapor phase. So that'll be the same concept as in number of moles in the vapor phase minus the number of moles in the vapor phase wanted. And now I'm going to put down those parameters. So we have our PF, it is now called our PF wanted, which is 200,000 pascals, which is 2e to the 5th. And then we also have our number of moles in the vapor phase wanted, which is 0.3. And then we also have our mass of water, or our total mass of water. So I'll just call that MW tot. And then that is 1 kilogram. And then we also have our initial pressure, which is 1 atmosphere, so 101,325 pascals. And then we also have our initial temperature, which is 298 Kelvin. Our goal now is to fill all of this middle section in with a bunch of equations in order to get to this point. So now we'll start with the moles of air, which is equal to the initial pressure minus the vapor pressure of the water at the initial temperature. So what we're going to do is we're going to use our object here, the Z, to use PVAP, which is the vapor pressure, with our temperature. And then that is minus the volume in the vapor phase, which is the V total. So we'll just do VT minus the total mass of water divided by the density of water. So again, we'll use our class or our object, and that'll be this at the initial temperature. And then all of this is divided by R times the initial temperature. Quick typo, this minus sign should be a multiplication sign. Sorry. So rewatching the video that I explained the return statement, I don't think I explained it all that well. But so basically we have two equations. These are our two equations, and these are our two unknowns. And so basically, when you type in here, the best way to type it, like we're trying to type it like we want our final pressure to equal 200,000 pascals. But you can't just type that in. So you have to give this a variable name. And so we gave that the PF wanted. And you also can't do this because it won't read it right. So you have to subtract it to the other side and then set this whole thing will get equal to 0. And then that will give you PF equaling 200,000 pascals. So next we are going to draw a relationship between our functions, or our equations, our two equations, and our two unknowns. So to do that, we'll do PF is equal to the partial pressure of air plus the partial pressure of water. Then we are going to do an equation for our moles in the vapor phase. So that's that. And then this will be our object. And then it'll be P, the vapor pressure, at the final temperature. And then that will be times the volume in the vapor phase divided by R times the final temperature. And then we, instead of using this and PW basically are the same thing. So we're just going to do PW equals Z dot vapor pressure of the final temperature. And then we are going to just replace this with PW. That just makes it easier. Now, that creates a relation between our final temperature, our first unknown, and our first equation, which is the final pressure. Now we're going to make a relation between the total volume and the moles in the vapor phase. So we're going to start with volume in the vapor phase is equal to VT minus, we'll just call it VL, so volume in the liquid phase. We also know that the volume in the liquid phase is equal to the mass over the density. So it'll be mass of water in the liquid phase divided by, and then this is also where the object comes in, the mass of or the density of water at the final temperature. So now we are going to make an equation for the mass of water in the liquid phase. So what that looks like is that is our total mass of water minus our mass in the vapor phase. And we know the mass of the vapor phase is the moles that was given to us right here times the molecular weight of water. So that'll look like wanted times 18 e to the negative 3. And that's our mass of water in the liquid phase. We are going to find the pressure of the air. And so I would type it up here, but I know that the PV equals nRT equation that involves this requires the volume in the vapor phase, and so we have to type it after so that it can calculate this first. And so this will look like this times R times the final temperature divided by volume in the vapor phase. Finally, we can go and run this guess that we were given in class as a pretty accurate guess. And we'll do that. And so basically what this is telling us is our final temperature has to be 366 Kelvin. And then it also has to be 12 liters in volume, because this is in cubic meters, and there's 1,000 liters in 1 cubic meter, and so this converts to 12 liters.